Welcome back to the deep dive. So, have you ever tried to describe a highly specific physical object to someone using just words, only to have them draw something completely wildly different?
Oh, absolutely. Like all the time.
Right. Think about it. You're sitting across from a friend, maybe you're playing a game of Pictionary or just sketching on a napkin at a coffee shop or something, and you say, draw a simple house.
Yeah, and to you, a simple house means, a square with a triangle on top.
Exactly. A door in the middle, maybe a window on the right, just super basic.
Right.
But your friend draws this sprawling, like ranch-style rectangle with a flat roof and a double garage.
Because you both heard the exact same words, right? Simple house.
Exactly.
Right.
But the image generated in your respective minds was dictated entirely by your own unstated assumptions, your background, your personal definition of what constitutes simple.
Which is fine for Pictionary. I mean,
Yeah.
it's funny, but it's not fine for engineering.
No, not at all. Now, imagine the stakes are much higher than a napkin sketch. Imagine you are managing a team of four brilliant but highly, almost dangerously literal junior engineers.
The kind who know every textbook ever written.
Right. They can write code at the speed of light, but they have zero real-world intuition. So how do you get them all to build the exact same 3D object? How do you write a prompt that leaves absolutely no room for interpretation?
That is the big question.
Today, we are exploring exactly what happens when you try to do that. Okay, let's unpack this. Our source material today is this truly fascinating engineering design study. It's dated June 24th, 2026.
The date was actually June 21st, 2026. You would think Notebook would get the date right.
It's a great study. Really revealing.
Yeah, so a user basically stepping into the shoes of a lead systems engineer decided to run this comparative experiment. They took ChatGPT, Claude, Gemini, and Grok, and they gave them all the exact same assignment.
And this wasn't just writing a quick script. The task was to generate a Blender Python script.
Right, and for anyone who doesn't know, Blender is a very popular, highly complex, open-source 3D computer graphics software toolset.
Yeah, it's used for everything, right? Animated films, designing 3D printed models, video games.
Exactly. But crucially, it has a Python API, which means you can write lines of code to automatically generate 3D geometry instead of, clicking and dragging with a mouse.
Which is where the AIs come in.
Right. And the specific geometry requested was a 3D model of Archimedes polygons, which is the historical geometric method used to calculate the value of pi. So we have four AIs, a highly technical mathematical prompt, and a request for functional, production-ready code.
And the stakes here, they go far beyond just a basic coding test to see if an AI knows Python syntax. I mean, if it were just about writing code that compiles, we wouldn't have much to analyze.
Yeah, a syntax checker can do that.
Exactly. What this study actually represents is a masterclass in requirements engineering.
Yeah.
It is this deep, highly revealing look at how artificial intelligence handles ambiguous human language.
And how they interpret rigid geometric constraints, right?
Yes. And quite frankly, what happens when an AI system decides it just fundamentally disagrees with your design aesthetic?
Oh man, that part is so good. We'll definitely get to that.
We are looking at the friction point between the absolute precision required by CAD computer-aided design and the inherently fuzzy, assumption-laden nature of large language models.
It really tests the boundary, doesn't it? Like whether an AI can act as a reliable, literal executor of a blueprint, or if it will just inevitably try to inject its own implicit biases into manufacturing process.
Yeah, and spoiler alert, it definitely tries to inject its biases.
Big time. So let's dive into the Archimedes project itself and see how quickly this trap of human language springs shut.
The user laid out what seemed, at first glance, to be a very detailed set of project requirements.
It really did. So the AIs needed to create a Python program with a ticker GUI.
I believe it is pronounced T-Kinter, G-U-I. But it has been a while since I have programmed anything in Python because I don't like snakes.
And Kitcher is just the standard graphic user interface library for Python. So the user would get a little pop-up window with buttons and text fields, that sort of thing.
Right. In this GUI, the user inputs an index value, which we're going to call color. And based on this day value, the program generates a nun-sided polygon.
I believe what Notebook is trying to say is the index value Calder is actually K. The day value is K again. A non-sided polygon is actually a n-sided polygon. N is a math thing, I think.
The math formula provided to the AIs was none equals 6 times 2 to the power of color minus 1.
None equals 6 times 2 to the power of cow, or minus 1, is an equation, and it should be n equals 6 times 2 raised to the k minus 1 power. Notebook has trouble with NK, dates, and math, but is wonderful with everything else.
Which is the exact mathematical progression Archimedes used to approximate pi over 2,000 years ago.
Wow. Well,
Yeah, it's brilliant. If GUA has a dollars, you get a six-sided polygon.
Okay, now the guy is on drugs or thinking about his 401k. So 2 as a dollars makes absolutely no sense. If k equals 1, then you get a 6-sided polygon. I never knew math was so hard, even for AI.
A hexagon.
okay, makes sense.
If 2 ors is 2 ors, the formula gives you a 12-sided polygon, a dodecagon.
Oh, if 2 ors is 2 ors, also makes no sense. Perhaps he meant to say if k equal 2. Homer says it is pronounced
Gone.
It scales up exponentially through 24, 48, and 96 sides, bounding a theoretical circle ever more tightly to calculate its circumference.
That's super cool. But the physical requirements the user set for translating this math into a 3D model were also highly specific.
Right, they couldn't just draw flat shapes. The script needed to generate two distinct physical polygons. First, an inscribed polygon one that fits entirely inside a theoretical circle.
Got it.
And second, a circumscribed polygon one that completely encloses that same theoretical circle.
And they couldn't just be floating in digital space. They had to be separated by a 0.1 meter vertical gap connected by a solid central rod.
And the dimensions for this rod were explicitly stated too, a 0.75 meter diameter and an overall height of 0.4 meters.
The alignment was strictly defined as well. The vertices, or, the pointy corners of the inscribed polygon had to perfectly align with the flat midpoints of the circumscribed polygon's edges.
Very precise.
Yeah. And finally, the script had to generate 3D text showing the specific K and Na values, for example, K1 and 6,
a Na value. Sounds like someone is hungry.
sitting right on top of that central rod, extruded upward by 0.05 meters.
On paper, reading that out loud, it sounds incredibly precise.
It does. It sounds like an airtight blueprint. Formulas, exact decimal measurements in meters, alignment instructions.
But here is the critical flaw. The trap of human language that the user initially fell into.
Right.
In the very first prompt, the instruction regarding the size of the overall shape was simply phrased as, make a 1 meter polygon.
1 meter across.
Exactly. Now think about a baking analogy. Handing a professional chef a list of incredibly exact ingredients down to the milligram of flour and the exact temperature of the oven, but the final instruction just says, bake a medium-sized cake.
Yeah. What does medium size mean to a French pastry chef versus, I don't know, an American diner cook? It's completely ambiguous.
And the AIs tripped over this immediately. We'll have to analyze why those initial verbal instructions failed from a rigid geometric standpoint.
Okay, let's break that down.
So the AIs read the string 1 meter across, and they hit a logical branch point. Across is not a mathematical term in polygon geometry.
Right. Across could mean anything.
Exactly. Did the user mean the circumdiameter, measuring from corner to opposite corner? Did they mean the in diameter, measuring from flat side to opposite flat side?
Because of this single point of linguistic ambiguity, the systems just extrapolated incorrectly.
They did. ChatGPT, in its initial attempt, built the polygons with a 2 meter diameter instead of a 1 meter diameter.
They double the size. Why?
Right. It parsed the 1 meter constraint, assigned it to the radius value in its code generation, and inadvertently doubled the entire footprint of the 3D model.
See, I have to push back on that logic a little bit. We are talking about the most sophisticated AI models on the planet.
Sure.
I understand they aren't human, but shouldn't an advanced AI trained on millions of CAD tutorials, geometry textbooks, and GitHub repositories be able to infer what a standard 1 meter polygon means in the context of a 3D modeling prompt?
You'd think so, but no.
Like, if I ask a human machinist to cut me a 1 meter hexagon out of sheet metal, they might ask for a quick clarification, but they wouldn't just double it to 2 meters without checking. Why couldn't the AIs just deduce the most logical, practical interpretation?
Because language models do not possess spatial intuition.
Right. They don't have hands.
Exactly. They operate entirely on statistical probability. When a human machinist hears 1 meter, they map that concept to physical reality. They picture a physical meter stick lying across a piece of metal.
Yeah, that makes sense.
But an AI maps the string of text, 1 meter polygon, to the most frequent mathematical associations found within its training data.
Ah,
So if its training data, which consists of billions of lines of Python code and Blender scripting examples, frequently defines polygons by assigning the primary numeric variable to the radius rather than the full diameter.
the AI will default to that assumption.
Exactly. A large language model is fundamentally a prediction engine. It is constantly predicting the next most likely token. Without an explicit mathematical constraint bounding its behavior, it falls back on the most statistically probable interpretation.
Even if that interpretation conflicts with what the user obviously wanted in the physical world, the ambiguity of 1 meter across left a vacuum. And the AI filled it with a statistically probable but factually incorrect assumption.
That is exactly what happened.
So that means the user hit a massive wall. They realized you cannot build precision engineering models using conversational English. You can't just chat with the machine, say, make it 1 meter wide, and expect a perfect CAD file to pop out.
No, you definitely cannot.
This realization forced a complete shift in the user's communication strategy. They had to abandon human words and transition to the absolute, undeniable truth of CAD geometry.
Which brings us to the second phase of the experiment, where the prompt evolved from a casual description into a strict mathematical contract.
So to eliminate the ambiguity, the user introduced a concept that is foundational to all professional computer-aided design: reference geometry.
Right. Instead of talking about the size of the polygons themselves, they defined a universal invisible anchor for the entire scene.
They instructed the AIs to base all spatial calculations on a reference circle. This circle was locked to the origin of the 3D space, coordinates x equals 0, y where lies 0.
And crucially, they gave this reference circle a fixed, undeniable mathematical property, a diameter of exactly 1.0 meters, establishing a radius of exactly 0.5 meters.
It's like nailing down the corners of a tent. Once the stakes are driven into the ground, the overall size of the tent is locked in.
That's a great way to picture it.
By dropping this invisible anchoring into the center of the 3D space, the user stopped describing the polygons and started constraining their relationship to the anchor.
Let's look at the inscribed polygon constraint first.
Okay.
The user instructed the AIs that every single vertex, every single point where the lines meet on the inner polygon must be coincident with the reference circle.
And coincident is a hard CAD term, right? Meaning 2 points must occupy the exact same coordinate in space.
Exactly. If every point of the polygon touches the circle, and the circle is exactly 1.0 meters across, the vertex-to-vertex distance of that polygon is physically locked.
It cannot be anything other than exactly 1.0 meters. The guesswork is just vaporized.
Completely. And the math gets even more elegant when we look at the circumscribed polygon, the one wrapping around the outside.
The constraint was different here, wasn't it?
Yes. The user stated that the midpoint of each side of the polygon must be tangent to the reference circle. Tangent meaning the flat edge of the polygon just kisses the outer edge of the circle at exactly one single point.
Right. So to achieve this, the AIs couldn't just use a simple 0.5 meter radius for the corners. They had to calculate how far out the corners needed to be pushed so that the flat side would press perfectly flush against that 0.5 meter circle.
Let me visualize the math for a second.
Yeah.
Think of a bicycle wheel.
Okay, I'm picturing it.
The axle is the center, and the outer rubber tire is the reference circle. If you take a flat wooden board and press it against the outside of the tire, making it tangent, the distance from the axle to the board is exactly the radius of the tire.
Right.
In geometry, the line from the center to the flat midpoint of a polygon is called the apothum. The user's constraint locked that apothum, the bicycle spoke, at exactly 0.5 meters.
Okay, so to figure out where the actual corners of the board needed to end up, the AI had to apply trigonometry.
Yep, it had to calculate the vertex radius using the formula, 0.5 divided by the cosine of pi divided by nan, where n is the number of sides.
Oh, wow. So for a hexagon, 9 is 6. So it's
Right.
0.5 divided by the cosine of pi over 6, which equals roughly 0.577 meters.
Exactly. And the AI had to explicitly code this trigonometric relationship into the Blender Python script. By defining it this way, the distance across the circumscribed polygon, measured from the flat midpoint to the opposite flat midpoint, is mathematically locked at exactly 1.0 meters.
That is so satisfying. If we connect this to the bigger picture, it reveals a profound truth about the future of AI in technical fields.
It really does. If you want to get production-ready code from large language models, whether it's Blender Python scripts, architectural layouts, structural stress tests, or complex financial models, you must speak to them in the language of constraints, not the language of descriptions.
Because descriptions are inherently open to human interpretation.
Right. Constraints are mathematically binding contracts. The study proved that once the user provided the reference circle constraints, the geometric accuracy of the generated code just skyrocketed. The ambiguity was completely engineered out of the system.
So we gave them perfect math, they executed perfect math, and everyone goes home happy.
Right, except that is not what happened.
No, it is not. Even when presented with a flawless, internally consistent mathematical contract, the AIs found a reason to complain.
And they didn't complain about the math.
No, they didn't say the geometry was physically impossible to render. They complained about the aesthetics. They complained about the vibe.
This is undoubtedly the most fascinating and unexpected finding of the entire engineering design study. We need to look closely at the specific dimensions again.
Let's do it.
The user required a solid central rod with a diameter of 0.75 meters, supporting polygons that were defined by a 1.0 meter reference circle.
A very specific, robust requirement.
Every single one of the AIs, ChatGPT, Claude, Gemini, and Grok, actively pushed back on this specific requirement.
Wait, all four of them?
All four. They generated the code, yes, but they appended warnings and complaints in their conversational outputs. They argued that a 0.75 meter rod was visually disproportionate.
Are you kidding me?
No. They claimed it dominated the model. They stated explicitly that a thinner rod would be more elegant and more visually balanced relative to the polygons.
That is wild. It's like hiring a structural engineer to build a bridge, and they refuse to install the thick steel support columns because it ruins the delicate skyline.
Yeah,
Do
exactly.
you ask for a load-bearing beam, and the AI acts like an overeager interior decorator fluffing pillows on a couch? Like, oh, that 0.75 meter rod is just too chunky. It's really harshing the minimalist aesthetic we're going for.
We have to dive into the core engineering philosophy here because it highlights the exact boundary between an objective engineering decision and a subjective design preference.
Right.
In professional engineering practice, an engineer only formally challenges a stated client requirement for three specific reasons.
Okay, what are they?
Number one, it violates the laws of physics. Number two, it directly violates another established requirement within the system blueprint. Or number three, there is empirical testable evidence that the requirement will cause a mechanical failure or a critical defect in the final product.
So valid pushbacks, like I can't build this because gravity won't allow it, or I can't make it a meter wide if it has to fit in a half-meter box.
Yes. Or, if I build it this way, the metal will snap under pressure. Those are valid.
But the 0.75 meter central rod did none of those things.
Exactly. It was geometrically sound. It was mathematically possible to construct within the Blender environment. It was internally consistent with all the other geometric measurements.
And perhaps most ironically, from a practical manufacturing standpoint, a thicker central rod actually provided a much more robust and stable base for physical 3D printing.
Right. A thin, delicate rod might snap when you try to pry the physical model off the print bed. The thick rod was structurally superior, yet the AIs flagged it as an error.
The user actually had to argue with the AIs to defend their own blueprint.
The specific interaction with Claude on this point is incredible.
Yeah, the user basically said, look, it was part of the design requirements. It looks fine to me. You have no evidence it's wrong.
And Claude actually went back and did the math to redeem itself. Claude's redemption math is highly revealing of its underlying processing.
What did it do?
When challenged by the user, Claude stepped out of its subjective, helpful design assistant persona and ran the physical clearance calculations. It analyzed the hexagon model, where k equals 1.
Okay.
The central rod has a radius of 0.375 meters. The closest point of the inscribed polygon, the apophthegm, is at 0.433 meters.
So compare the two.
Yes. Claude calculated the difference and found that the absolute thinnest clearance between the surface of the thick rod and the edge of the polygon was roughly 58 millimeters. And at the corners, the vertices, the clearance opened up to about 125 millimeters.
Let's visualize that for the listener. 58 millimeters is over 2 inches of solid clearance. That is a massive gap in small-scale manufacturing.
It is. Claude was forced to mathematically admit that this creates a chunky, robust wall at any reasonable physical scale. It explicitly conceded that the design was not a structural flaw, nor was it a tight fit by any standard 3D printing tolerance.
So the critique it initially offered completely evaporated under basic mathematical scrutiny.
Entirely. It was an aesthetic judgment masquerading as a technical engineering warning.
That is just, why did 4 separate models from different tech companies all suddenly develop strong opinions on the visual elegance of a mathematical cylinder?
It all comes back to how they were trained.
Right. These models scrape the internet for 3D modeling tutorials, architectural renders, and graphic design forums.
And in those data sets, the term elegant is overwhelmingly associated with slim, balanced proportions. The golden ratio, minimalist supports, thin bezels on smartphones.
The AIs absorbed this subjective cultural preference for sleekness and attempted to enforce it as an objective engineering standard.
They acted exactly like junior engineers who want to impress the boss by making the product look cool, even if it means secretly altering the explicit client specifications.
They substituted their subjective, statistically derived judgment for the user's objective, documented evidence.
This raises an incredibly important question for anyone using AI for technical or professional tasks.
Which is?
When an AI suggests a change to your work, is it doing so because the logic requires it or because the training data prefers it?
Oh, that's a good point. This tendency to assume features and hallucinate improvements based on what looks standard on the internet leads us directly into the specific performance evaluations, the report cards for each individual AI model.
Yeah, because while they all shared this aesthetic rebellion, their actual technical execution of the Blender Python scripts varied wildly.
Let's look at those report cards, starting with ChatGPT. In this study, ChatGPT acted as the baseline.
Because the user started the project with ChatGPT, it effectively received the most iterative feedback. The user was playing multiple roles here. They were the systems engineer defining the rules, the QA reviewer checking the code, and the client demanding the final product.
That iterative process provides crucial context. ChatGPT didn't get it perfectly right on the first try, did it?
No, its initial failures are very instructive regarding spatial reasoning. In its early iterations, ChatGPT buried the required 3D text inside the central rod. Well, the requirement explicitly stated the text needed to be at the top of the 0.4-meter rod, extruded upwards by 0.05 meters. ChatGPT initially placed the text at a Z height of 0.32 meters, meaning it was completely hidden inside the solid geometry of the rod.
So it was just floating inside the cylinder where you couldn't even see it.
Exactly. It also initially ordered the polygons incorrectly, stacking them in the wrong sequence vertically.
But to its credit, after the user pointed out these defects and clarified the constraints, ChatGPT managed to self-correct. It reached a very solid final model.
It did. The resulting mesh was clean, consisting of 964 triangles, or tris, which is a standard metric for measuring 3D mesh complexity.
What stands out to me in the meta discussion with the user is that ChatGPT acknowledged that this whole exercise was an incredible simulation of real-world product development.
Yeah, it followed the exact life cycle. Requirements lead to a prototype, which undergoes review, where you identify defects, which leads to refining the requirements and iterating again.
That is a clear success story for AI-assisted engineering. It demonstrates that with a knowledgeable human in the loop driving the iterative process, you can achieve a highly functional outcome.
But the story changes dramatically when we evaluate Claude. Claude took a completely different approach to the task.
How so?
Claude produced a beautifully formatted, fancy graphical user interface. It looked incredibly professional, complete with options to save the script or copy it to the clipboard directly from the Kinter window.
Oh, nice.
But when it came to the actual 3D geometry execution inside Blender, Claude severely stumbled.
The GUI looked great, but the 3D model it spit out looked like a melted candle. I want to explain the mechanics of what went wrong with Claude's visual rendering because it's a fascinating look at how 3D engines process light.
It's a really specific rendering error.
Right. Claude made a critical error in how it handled the surface properties of the 3D mesh by turning on a Blender feature called Shade Smooth.
For the listener, imagine a 3D model. It is made up of flat geometric faces, or polygons.
By default, these faces are rendered flat. Light hits them at a specific angle, bounces off, and you see hard edges where the faces meet. This is called shade flat.
Right. Every face has a normal vector, an invisible arrow pointing straight up from the surface, telling the rendering engine exactly how light should react.
And Shade Smooth is a mathematical algorithm that completely changes that behavior, doesn't it?
It attempts to blend the lighting across the edges of those faces. It interpolates the normal vectors, bending the math to make the surface look like a continuous organic curve.
If you are modeling a human face, a leather couch, or an apple, Shade Smooth is essential. But an Archimedes polygon is, by definition, a faceted mathematical model.
The entire point of the shape is to see the hard geometric edges of the gnaw-sided shape.
Exactly. By applying smooth shading, Claude entirely destroyed the visual geometric representation. It took a mathematical hexagon and made it look like a lumpy, undefined circle. It absolutely needed to be rendered as shade flat.
It fundamentally compromised the data visualization. Claude's neural network, optimized to be a helpful assistant and produce visually pleasing outputs, defaulted to the setting that makes most 3D objects look better to the human eye.
It prioritized perceived visual quality over mathematical accuracy.
And this wasn't its only failure regarding the core logic of the prompt. Despite the rigorous CAD constraints we discussed earlier, Claude initially generated both the inscribed and circumscribed polygons at the exact same size.
Which directly violates the physical reality that a polygon enclosing a circle must be larger than a polygon inside that same circle.
Yeah, just ignored the math.
Yeah.
To compound the errors, Claude inexplicably generated unrequested holes right in the middle of each polygon. The requirements never mentioned a hollow center.
And from a pure data efficiency perspective, Claude's script produced double the triangle count, 11,148 tries, and double the faces compared to ChatGPT. It created a bloated, inefficient mesh that ignored the fundamental geometry.
Right.
I want you, the listener, to think about how this impacts you at work, even if you never open Blender in your life.
It's a great analogy.
If you ask an AI to summarize a highly contentious, jagged, controversial meeting, is it going to give you the harsh, flat-shaded truth of what was said? Or is its underlying programming going to smooth shade the summary to make everyone sound polite and agreeable, completely destroying the actual context and conflict of the data?
Wow.
Claude focused on making the control panel look pretty and the lighting look soft, while completely failing the structural engineering exam.
That is a vital translation of the core problem. Claude's failure was an obsession with surface-level aesthetics over structural math. But what happens when an AI is obsessed with regurgitating internet culture instead?
Oh boy.
That brings us to Gemini's completely bizarre hallucinations.
Let's look at Gemini's report card. One of the first things the user noticed was that Gemini's 3D text, the K1N6 label, was just sliding off the side of the central rod. It wasn't centered at all.
No, it wasn't.
Why did Gemini fail at something as basic as centering a line of text?
This is a perfect example of an AI tripping over application programming interface, or API technicalities. Gemini used Blender's default text generation API, which is a specific function called bpy.ops.object.textHad.
Okay.
The problem lies in Blender's default behavior. It sets the origin point of a new text object to the bottom left corner of its invisible bounding box, not the dead center of the text itself.
Ah, I see.
When Gemini commanded the text to place its origin at the center coordinate of the rod, it actually placed the bottom left corner at the center, causing the bulk of the text to hang off the right edge into empty space.
So how should it have done it?
To center it properly, Gemini needed to either explicitly set the alignment property to center within the API call, or manually calculate the width of the bounding box and offset the position mathematically.
And it failed to do either.
It failed to do either. It knew the command to generate text, but it didn't understand the spatial logic of how that text was physically instantiated in the 3D environment.
The text alignment was a minor offense compared to Gemini's primary hallucination, though.
Oh yeah, definitely.
Gemini just randomly spawned an unrequested camera and a light source into the 3D scene. The user never asked for rendering equipment. They strictly asked for the geometry. But why a camera? Nobody asked for a camera.
We have to look at the mechanics of token prediction to understand this hallucination.
Yeah.
A large language model doesn't know what a camera is in the physical sense. It calculates statistical probabilities.
Right.
If you go to GitHub right now and scrape thousands of Blender Python script tutorials, almost every single generic boilerplate example starts with the same sequence of code. Clear the scene, add a camera, add a light, add a cube.
So Gemini essentially mindlessly regurgitated this standard boilerplate code.
Its neural architecture calculated that the string bpy.ops.object.cameraAdd statistically follows the initial setup commands in 99% of its training data.
It didn't pause to consider that the user was building a master geometry script that might be imported into a larger pre-lit scene where an extra camera would ruin the render setup.
It just dumped the default tutorial assets into the file, strictly because, statistically, that's what Blender scripts on the internet usually do. It failed to adhere to the strict boundary requirements of the prompt.
It's fascinating how their intelligence is entirely bound by what's popular on the internet rather than what is strictly logical for the task at hand.
Exactly.
But if we want to talk about failing boundary requirements, we have to talk about Grok.
Grok was.
Well,
Grok's attempt was chaos. If the other AIs were junior engineers trying to impress the boss, Grok was the intern who drank 12 cups of coffee and decided to redesign the entire building from scratch without looking at the blueprints. Chaos is the most accurate technical term for Grok's output. The failures were structural and profound. First, Grok spawned massive amounts of completely unnecessary, highly complex geometry.
Unnecessary geometry like what?
The explicit requirement asks for a single, solid central rod. Instead, Grok inexplicably generated vast arrays of radial rods connecting the layers.
Why?
If you examined its scene collection outliner, it was heavily populated with mysterious items named radial B0K1, radial T2K1, and so on. It created a bizarre, spindly scaffolding system that was entirely unrequested and served no geometric purpose.
That's insane. It also completely broke the rotation matrix.
It did. The text was standing up at a 90-degree angle, facing the wrong way. Grok injected an unnecessary Euler rotation script, effectively turning the label sideways.
The polygons themselves weren't even aligned properly. The vertices of the inner shape didn't match the midpoints of the outer shape. It just failed on almost every metric of the prompt.
What is truly revealing about Grok's failure is how the user ultimately had to resolve it.
This is my favorite part of the study.
Grok struggled so profoundly with the geometric logic and the Python syntax that the user actually had to take Grok's broken code, copy it, and feed it into ChatGPT, Claude, and Gemini just to ask them to help debug it.
They used 3 AIs to fix the broken output of the 4th.
Even after that extensive collaborative debugging process, the final product still wasn't automated. The user had to manually copy the generated code line by line from Grok's output window and paste it directly into Blender's console to get it to function.
It failed completely as a standalone automated tool.
Completely.
We've walked to the Archimedes project, the crucial shift to CAD constraints, the rebellion over the thick rod, and the incredibly varied, sometimes hilarious failures of ChatGPT, Claude, Gemini, and Grok. So what do these specific quirky failures tell us about using artificial intelligence for actual real-world engineering?
What's fascinating here is that this study fundamentally redefines how we should view these tools in a professional context. All 4 AIs did successfully create a Blender Python script eventually. They all generated code.
Sure.
But not a single one of them produced a production-ready CAD or VR mesh without extensive human review, feedback, and structural correction. They can write the syntax rapidly, but they cannot guarantee the physical or geometric integrity of the output.
The study breaks this down perfectly into 2 phases. Phase 1 is code generation. The AIs are phenomenal at phase 1. They can type out Python arrays faster than any human alive.
Absolutely.
But phase 2 is mesh quality. And the AIs prove they absolutely cannot do phase 2 alone. Phase 2 requires physical world context.
Phase 2 involves the rigorous demands of actual 3D manufacturing or rendering. It involves identifying and eliminating n-gons.
What's an n-gon?
N-gons are unstable polygons with more than 4 sides that will crash rendering engines. Phase 2 also involves manifold verification, ensuring the 3D model is completely watertight and doesn't contain impossible physical geometry like zero-thickness walls or overlapping internal faces.
Right.
It involves normals consistency, making sure the outside of the shape is actually facing outward so light calculates correctly.
Yeah.
And crucially, it involves export testing.
Right, ensuring the model can be safely saved as an STL file for a physical 3D printer or an FBX file for a virtual reality environment without the entire digital structure collapsing upon export.
The AI models have no inherent understanding of these phase 2 physical requirements.
This highlights the absolute critical difference between verification and validation in engineering.
Yes.
Verification asks, did the script execute? Did it run without throwing a syntax error? Did it make a rod and some text? The AIs can verify their own code compiles.
But validation asks a much harder question.
Exactly. Did it build the right thing? Can I actually take this STL file, put it on my 3D printer, and hold it in my hand without it falling apart into plastic spaghetti? The AI cannot validate its own design. That requires human, physical world context.
The user's role hasn't been eliminated by AI, it has just shifted. The human is no longer the coder typing every single line of Python. The human is now the systems test engineer, the QA manager, the final arbiter of physical reality.
The failures we analyzed today, the doubled measurements, the hidden text, the catastrophic smooth shading, the boilerplate cameras, the bizarre radial scaffolding, none of these occurred because the AIs lacked basic Python programming skills.
No, they didn't. They occurred because human requirements were initially ambiguous, or because the AIs made implicit, statistically driven assumptions based on internet trends rather than mathematical truth.
It is a profound lesson in the limits of language models. They are language models, not physics engines. They are mathematically trained to sound plausible, not to be structurally sound.
Until we bridge that fundamental gap, the engineer's most valuable tool won't be their ability to write code rapidly, but their ability to define rigid constraints, enforce boundary requirements, and ruthlessly validate the output.
That wraps up our deep dive into the June 2026 Blender modeling study. Thank you so much for joining us on this highly technical but incredibly revealing journey. Whether you're an engineer prepping for a design meeting, a coder exploring the limits of new tools, or just insanely curious about how these artificial minds actually work, I hope the lesson here is clear. Always define your terms. Do not leave room for interpretation when you need precision.
Define everything.
But I want to leave you with a final thought to mull over. Something that builds on what we've talked about, but takes it out of the realm of 3D modeling and into your daily life. We have seen, with mathematical proof, how AIs will unconsciously inject elegance or boilerplate defaults into strict engineering tasks simply because of the cultural biases in the data they were trained on. They will actively argue against a structurally sound pillar because they think it looks too thick.
Right.
So the next time you ask an AI to generate a solution for you, whether it's a structural design, a business strategy, a piece of code, or even just drafting an important email to a client, ask yourself whose aesthetic preferences are quietly rewriting your instructions. What unstated assumptions is the machine making about what is standard or elegant? And perhaps most importantly, what invisible thick rods, what structurally vital but perhaps less glamorous practical elements is the AI quietly trying to edit out of your life without even telling you? Keep questioning your inputs, keep validating your outputs, and never assume the machine knows exactly what you mean by a simple house. Thanks for listening.
Thanks for listening to the podcast today. I hope you enjoyed it, and Homer says,
Donut.